All right, folks, continuing our study of looking at limits in this section, section 2.4, we're going to look at what are called infinite limits. And then parenthetically, I have this crazy looking collection of letters, IWOB slash DWOB. So let's try to see what that's trying to communicate to us. So to start us off in looking at infinite limits, let's look at the graphs of the functions f of x equals 1 over x and f of x equals 1 over x squared. Well, there are the graphs. On the left is f of x equals 1 over x, and on the right is f of x equals 1 over x squared. So let's say we wanted to find the limit as x approaches 0 from the right side of 0 of 1 over x. So, it looks like as x approaches 0 from the right side, try to highlight this here, it looks like the y values are getting larger and larger and larger. The y values are increasing, and there's actually no bound to their increasing behavior. So the y values are increasing without bound, IWOB. So technically they're increasing without bound, IWOB. Now what we're going to do is we're going to use the infinity symbol. You're all familiar with that. We're going to use that to communicate the behavior that it's increasing without bound. So, going forward, I would say the limit as x approaches 0 from the right side of 0 of 1 over x equals infinity. Do not treat infinity as a number. It is a concept. It is a concept that's communicating a behavior, an increasing without bound behavior. Well, what if we're asked to determine the limit as x approaches 0 from the left side of 0 of 1 over x? Well, as I try to get closer to 0 from the left side of 0, it looks like the functional values are decreasing. And there's no bound. They're decreasing without a bound. That limit is a DWOB. But going forward, we are going to use the symbol negative infinity. So the limit as x approaches 0 from the left side of 0 of 1 over x, that limit is negative infinity. Again, negative infinity is not a number. Don't treat it as a number. It's a concept. It's telling you that something is decreasing without bound. There's no end to the decreasing behavior. Well, now that we've identified the limit as x approaches 0 from the right side of 0 is infinity, and the limit as x approaches 0 from the left side of 0 is negative infinity, that means the limit as x approaches 0 of 1 over x, well, the limit does not exist. Remember, in order for the limit to exist, the left-hand limit and the right-hand limit must be approaching the same thing. Well, negative infinity and infinity are not the same thing, so the limit does not exist. All right, let's analyze 1 over x squared. So look at the limit as x approaches 0 from the right side of 0 of 1 over x squared. All right, do you see that that's an increasing without bound behavior? It's an IWOB, or we would use infinity to say the limit as x approaches 0 from the right of 1 over x squared is infinity. Then what's the limit as x approaches 0 from the left side of 0 of 1 over x squared? I mean, it looks like as I try to get closer to 0 from the left side, it looks like the functional values are increasing without bound. Yeah, that limit is infinity. So what does that make the limit as x approaches 0 of 1 over x squared? Well, since the left side limit and right side limit are exhibiting the same behavior, we would say the limit as x approaches 0 of 1 over x squared is infinity. All right, now this is a technicality point, folks. Technically speaking, all of those limits are it does not exist because, infinity is not a real number. However, we're going to use the symbol infinity to communicate the behavior IWOB, and we will use the symbol negative infinity to communicate the behavior DWOB. So these limits, because we're going to have limits that have results of infinity or negative infinity, they're called infinite limits. In other words, infinite limits are ones where as x approaches a, the functional values are approaching infinity or negative infinity. Now, if you look back at those graphs, you may have noticed that the y-axis was serving as a vertical asymptote for the graph. I mean, there is a connection between vertical asymptotes and infinite limits. So this is a classic definition. It says if the limit as x approaches a of f of x is positive infinity or negative infinity, if the limit as x approaches a from the right side of a of f of x is positive infinity or negative infinity, or the limit as x approaches a from the left side of a of f of x is positive infinity or negative infinity, then the line x equals a is a vertical asymptote for the graph of f. Okay, so now what we tend to do, though, is we tend to turn this around and say, hey, if we know where there is a vertical asymptote, then we know a limit. If we know there's a vertical asymptote for the graph of f, then we know what a limit would be. So it's going to be kind of important for us to be able to distinguish between values of the independent variable, most of the time that's x, that's producing a vertical asymptote versus when it's producing a hole in the graph. So you may have seen this in college algebra, but I thought, you know what, let's review it here real quick. So first thing we'll do, we have a function. We're going to determine values of the independent variable that makes the denominator equal 0. Any value of the independent variable that makes the denominator 0 is producing either a vertical asymptote or a hole. If the numerator does not equal 0 for a value of x that makes the denominator equal 0, then that value is producing a vertical asymptote. However, if the numerator equals 0 and the denominator is equal to 0 for a value of the independent variable, well, think about that. You'd have 0 over 0. That's an indeterminate form. Well, then that value is producing a hole. So let's look at an example here. I'd like you to get this written in your notes because it's a graph of some function g. You're being told there are vertical asymptotes at x equals 2 and x equals 4. So we are just going to use the graph to determine these limits, and there are 6 of them. So get this into your notes because, I'm going to head off to the chalkboard and work through it. Hey folks, in this example, we were given the graph of that function, g of x. We were also told there were vertical asymptotes at x equals 2 and at x equals 4. And, I've put those in there with the red dashed lines. And we're supposed to analyze the following limits. So part A, the limit as x approaches 2 from the left side of 2 of g of x. All right, so here's x equals 2, so we're approaching 2 from the left side, and as we do that, it looks like the function values are increasing without bound, so we would say the limit is infinity. Part B, the limit as x approaches 2 from the right side of 2. All right, so we come to the right of 2, we'd be here on the graph. As we approach 2 from the right side of 2, it looks like the function values are decreasing without bound. We represent that with negative infinity. So now part C is the limit as x approaches 2 of g of x. Remember, in order for the limit to exist, the left-hand limit and the right-hand limit have to be doing the same thing. They have to be approaching the same thing. Well, the left-hand limit's approaching infinity, the right-hand limit's approaching negative infinity. Those are not the same thing. So for part C, the limit does not exist. Part D, the limit as x approaches 4 from the left side of 4. So let's come over here and look at that. So here's 4. So I'm approaching 4 from the left side. It looks like as I get closer and closer to 4 from the left side of 4, it looks like those function values are decreasing without bound. So this limit is negative infinity. Part E, the limit as x approaches 4 from the right side of 4. Alright, so I come to the right of 4, and I'm approaching 4 from the right side. It looks like those function values, as I get closer and closer to 4 from the right side, it looks like those function values are decreasing without bound. Negative infinity is the limit. So then part F, the limit as x approaches 4. Well, since the left-hand limit is negative infinity, the right-hand limit is negative infinity, they're approaching the same thing, we say the limit in part F is negative infinity. So, at this time I'd like you to practice one of these. So in the exercises, excuse me, do number 10. So pause the video, go into the exercises, do number 10, and after you do number 10, restart the video, and I'll be here at the board working through it. All right, folks, so number 10, you were given the graph of y equals p of x, and then part A, you were asked to determine the limit as x approaches negative 2 from the left side of negative 2. So when I approach negative 2 from the left side of negative 2, it looks like we're decreasing without bound. So the limit is negative infinity. Part B, what's the limit as x approaches negative 2 from the right side of negative 2? So I come to the right of negative 2, I approach negative 2 from the right side, and it looks like, again, we are decreasing without bound. So the limit is negative infinity. Which means in part C, the limit as x approaches negative 2, since these are the same, the limit is negative infinity. All right, part D, what's the limit as x approaches 3 from the left side of 3 of p of x? All right, so I come over here, I approach 3 from the left side, and it looks like the functional values are decreasing without bound. So this limit is negative infinity. Part E, the limit as x approaches negative 3 from the right side of negative 3. So oh, I'm sorry, this is supposed to be a 3. And that's supposed to be a 3. So when I approach 3 from the right side, so I approach 3 from the right side, it looks like it's another decrease without bound. The limit is negative infinity. And that means the limit as x approaches 3, since these are the same, the limit is negative infinity. So hopefully you're seeing, these vertical asymptotes really help us determine the limits. So let's head on back to the slides and see what's in store for us next. All right, folks, as we just saw in this example and in number 10 that I asked you to practice, our knowledge of vertical asymptotes is telling us the limits. So that's the power of knowing where vertical asymptotes occur. So in this example, I'm giving you a function f of x equals x minus 3 over x squared minus 9. let's determine where this function would have a vertical asymptote, where this function would have a hole. So write this example into your notes because I'm heading off to the chalkboard to work through it. All right, this is really an old college algebra type question, but it's important in calculus. Being able to determine where the graph of a function would have a hole in the graph versus where there's a vertical asymptote. So this example, I gave you the function x minus 3 over x squared minus 9 and said, where will we find a vertical asymptote or asymptotes, and where will we find a hole or holes? So remember the key, you have to determine what makes the denominator 0. So this denominator is 0 at -3 and at 3. So right now I know on the graph of that function at an x value of -3 the graph either has a hole or it has a vertical asymptote. At x equals 3 the graph has a hole or a vertical asymptote. So once you determine what values of x are candidates for vertical asymptote or hole, remember this is how you determine if it's a vertical asymptote or a hole. So for x equals -3, we know that makes the denominator 0. What's the numerator? If -3 goes into x into the numerator, what do you get? Do you get 0 or non-zero? Well, when -3 comes in here for x, you get -6. So for an x value of -3, the denominator 0, the numerator is not 0. So that tells me we have, I'm going to abbreviate, a vertical asymptote at x equals -3. For x equals 3, okay, that makes the denominator 0. What about the numerator? Well, for that value of x, the numerator is also 0. So it's a value of x that makes the denominator 0 and the numerator 0. That tells me that the graph has a hole at x equals 3. And before we go further, just think about what this tells us at this point in time. Since we know there's a vertical asymptote at x equals -3, we know the limit as x approaches -3 from the left side and the limit as x approaches -3 from the right side. We know those limits are either infinity or negative infinity. Because we know there's a hole at x equals 3, I mean for an x value of 3 you would have 0 over 0. You know we could find the limit by doing the techniques we just saw in a previous section. You know, it's indeterminate form, 0 over 0. So we could find the limit as x approaches 3 using old techniques, some algebra magic. So being able to classify where you have a vertical asymptote or a hole is really important. In fact, I would like you to do this one now. Same directions. Where do you have a vertical asymptote? Where do you have a hole? And I would like you to analyze the function x plus 2 over x squared minus x minus 6. So pause the video, analyze that function, determine where the graph would have a vertical asymptote and where the graph would have a hole. When you're done doing it, I'll be here at the chalkboard working through it. Alright folks, I just gave you the function x plus 2 over x squared minus x minus 6. I said, where does the graph have a vertical asymptote? Where does the graph have a hole? So remember, the key is determining the values of x that makes the denominator equal 0, because that's producing a hole or a vertical asymptote. So I would start off, well, I guess I'll factor the denominator. See, I think it factors to x minus 3 times x plus 2. Alright, now I can see there are two values of x that makes the denominator 0. x equals 3, and x equals negative 2. So let's analyze each one of those separately. So x equals negative 2. X equals negative 2. That makes the denominator 0. It makes the numerator 0. Because it's a value of x that makes the denominator 0 and the numerator 0, we know the graph has a hole at x equals negative 2. All right, let's analyze x equals 3. We know x equals 3 makes the denominator 0. X equals 3 makes the numerator 5. So it's a value of x that makes the denominator 0, but the numerator is not 0. So there is a vertical asymptote at x equals 3. All right, hopefully you got that, folks. Let's head back to the slides and see what is next. All right, as you heard me say in the last example, and then that function that I asked you to practice the same concept, being able to identify where a function has a vertical asymptote means we're going to know what a limit should be. We know that if there's a vertical asymptote at x equals negative 3, for example, we know the graph of a function has a vertical asymptote at x equals negative 3. Then we know the limit as x approaches negative 3 from the left side is either positive or negative infinity. And as you approach negative 3 from the right side, the limit is either positive or negative infinity. So now to help us kind of tighten this up a little bit, and how we can determine if it's a positive infinity or negative infinity, let's consider any fraction that has the form a over b. Doesn't matter what the numerator is, doesn't matter what the denominator is, as long as the denominator isn't 0. But, any fraction of this form could be representing a rational function. Doesn't matter, just any fraction of the form a over b. If the numerator is not 0, and the denominator is approaching 0 from the right side of 0, so it's a positive number really close to 0, like say 0.0001, then a over b is approaching infinity, as long as a does not equal 0. If a is not 0 and b approaches 0 from the left side of 0, then a over b is negative infinity. I mean, I could write down a lot of cases here, but what I'm trying to get across is how we can analyze a function, say, like f of x equals 13 plus x over x. So if we're asked to determine the limit as x approaches 0 of 13 plus x over x, just kind of analyze this. You can think, all right, for an x value close to 0, from the right side of 0, the numerator is close to 13. That's a positive number. The denominator is close to 0, but it's going to be positive. So positive divided by positive, that gives us the limit to be positive infinity. I mean, we know from the function that x equals 0 is a vertical asymptote because it's a value of x that makes the denominator 0, but the numerator is not 0. On the other hand, if we're looking at the limit as x approaches 0 from the left side of 0, so say negative 0.001, the numerator, you can think, the numerator is still going to be close to 13. It's a positive 13. The denominator is going to be close to 0, but it's a negative number. Positive divided by negative is negative, so that limit would be negative infinity. So it's kind of like a little number sense on how to look at these things. And let's practice this just a little bit. So for this example, we're going to determine 3 limits. the limit as x approaches negative 2 from the right side of negative 2 of x minus 4 over x times x plus 2. In part B, the limit as x approaches negative 2 from the left side of negative 2 of the function x minus 4 over x times x plus 2. Then in part C, once we do A and B, we'll be able to answer part C. What is the limit? So, get this written in your notes. I'm going to head off to the chalkboard to work through it. Before I go, though, please note that for all three parts, x equals negative 2 is a vertical asymptote for the graph of the function x minus 4 over x times x plus 2. And that tells me that right now I know for parts A and B, my answer has got to be either positive infinity or negative infinity. So let's head off to the board and figure out which it is. All right, folks, in this example, we're asked to determine some limits. And before I came over to the chalkboard, I did point out to you that for the function x minus 4 over x times x plus 2, that x equals negative 2 is a vertical asymptote for the graph. That's because negative 2 is a value of x that makes the denominator 0, but the numerator is not 0. That tells me that my answer for part A is one of two things, infinity or negative infinity, because I know there's a vertical asymptote. It tells me my answer for part B is either infinity or negative infinity. So what we just kind of discussed, let me kind of run that through you, run that each one of these through that process. So let's think. As x approaches negative 2 from the right side of negative 2, so we're a little bit larger than negative 2. Negative 1's a little bit larger than negative 2, but we're a little bit larger than negative 2. The numerator, if you put a number in that's a little bit larger than negative 2, the numerator would be a negative number. The denominator, well, x would be a negative number. And x plus 2, well, x plus 2 would be a positive number. If you think of a number that's just a little bit larger than negative 2, say negative 1.9, that would be positive. So check it out. The numerator is negative. The denominator is a negative times a positive. Well, negative times positive is negative. So this would be a negative divided by a negative, which is positive. We already knew the answer here, because of a vertical asymptote, had to be negative infinity or positive infinity. Since this is positive, we conclude that this limit is positive infinity. Let's do the same type of analysis on part B. So part B, we know our answer is either negative infinity or positive infinity, because negative 2, x equals negative 2 is a vertical asymptote. So in part B, x is approaching negative 2 from the left side of negative 2. So we're a little bit smaller than negative 2. So think of something that's a little bit smaller than negative 2 going in for the x's. Well, the numerator is negative. This x would be negative. This factor, x plus 2. So if you're a little bit to the left of negative 2, say negative 2.1, negative 2.1 plus 2, well, that would be a negative number. So check it out. The denominator would be a negative times negative, which is positive. The numerator is negative. So negative divided by a positive, that's negative. This limit is negative infinity, which means in part C, the limit as x approaches negative 2. Because these are not the same thing, the limit does not exist. And I would be remiss if I didn't say, I personally, after I do this analysis, I personally would quickly use my calculator to graph x minus 4 over x times x plus 2 to visually confirm these limits. So, you know what, I'd like you to practice this type of analysis that we just did. So what I'd like you to do here is in the exercises, section 2.4 exercises, I would like you to pause the video, do number 32, then after you do number 32, start the video, and I'll be here working through the solution. Hey folks, at 32 it looks like parts A, B, and C, the function we're dealing with is x minus 2 over x to the fifth minus 4x cubed. In part A, we're trying to analyze the limit as x approaches 0 of the function. Part B, the limit as x approaches 2 of the function. And then part C, the limit as x approaches negative 2 for the function. So here's where I'd begin. I would begin by completely factoring the denominator. So when I completely factor the denominator, so folks, here in the denominator I'd factor out an x cubed. That would leave me with an x cubed times the quantity x squared minus 4. X squared minus 4, that factors to x plus 2 times x minus 2. So the complete factorization is x cubed times x plus 2 times x minus 2. Alright, so 0. It is a value of x that makes the denominator 0, thanks to this factor. But the numerator is not 0. So I know x equals 0 is a vertical asymptote. So I need to analyze two things before I can answer the limit. I need to analyze what's the limit as x approaches 0 from the left side of 0, x minus 2 over x cubed times x plus 2 times x minus 2, and what's the limit as x approaches 0 from the right. And since x equals 0 is a vertical asymptote, I know this limit is either infinity or negative infinity. I know this limit is either infinity or negative infinity. So let's try to analyze like we just did in this last example to see if it's infinity or negative infinity. So as x approaches 0 from the left side of 0, well, when I approach from the left side of 0, I'm a negative number. I'm real close to 0, so say negative 0.001. That's negative, but it's close to 0. So I think of a number like that going in here for x. Well, the numerator would be a negative number. X cubed, well, a negative number cubed is negative. Negative number plus 2, so we're talking about a negative number close to 0, plus 2, that's going to be positive. And then a negative number minus 2 is negative. So check it out, folks. The denominator would be a negative times positive times negative. Negative times positive times negative is positive. The numerator's negative, so negative divided by a positive is negative. This limit is negative infinity. Whereas here I'm approaching 0 from the right side of 0. So I just think of a number that's positive but close to 0, say 0.0001. When that comes in here for x, well, the numerator, it's going to be negative. Denominator, well, a positive number cubed is positive. A positive number plus 2 is positive. A small positive number minus 2, well, that's negative. So the denominator would be a positive times a negative. That's a negative. The numerator's negative. So negative divided by a negative is positive. So this limit is positive infinity, which means the limit we were asked to find does not exist. The left side limit and the right side limit are not approaching the same thing. All right, continuing on, part B. Well, the first thing I would do is factor the denominator. So let me go ahead and get the denominator factored. See, the factorization is x cubed times x plus 2 times x minus 2. Notice here, 2 is a value of x that makes the denominator 0, but it also makes the numerator 0. So we have a hole in the graph. We have the indeterminate form 0 over 0. And we've already done the first step. You know, we substitute, we got 0 over 0, and we've done the algebra magic. I mean, check it out, folks. The x minus 2's can cancel, which leaves us with the limit as x approaches 2 of 1 over x cubed times x plus 2. Substitute in the 2, and see, 2 cubed is 8, 2 plus 2 is 4, 8 times 4 is 32. So hopefully you got the limit to be a 1 over 32. Okay, part B, again, the first thing I would do, you know, factor, I have the factorization for the denominator. It's x cubed times x plus 2 times x minus 2. Negative 2 is a number that makes the denominator 0, but the numerator is not 0. So we know there's a vertical asymptote at negative 2. In order to determine if the limit exists, we need to look at, well, we need to determine the limit as x approaches negative 2 from the left side of negative 2, and the limit as x approaches negative 2 from the right side of negative 2. Oops. And if we do our analysis approaching negative 2 from the left side of negative 2, I think you would get that this limit is infinity, whereas this limit is negative infinity, which tells us the limit does not exist. And again, folks, once I've done all this analysis, I would graph the function just to make sure that my analysis is correct. So, you know, graph it and see. Well, folks, that's it on this section. So, you know, at this time, you can do the exercises. So, head off, section 2.4, do all the exercises. Thanks for watching.